Let's apply the derivative process to the power function. And we'll start with the easiest power, 2. We're going to feed that through the derivative process. This is the notation we use for the derivative now, just a little slash up in the corner. That's the difference quotient. And then we derive h to 0 with a limit. Now I need a point and a function to start it off. The mapping notation tells us both. So I'll plot that information. I go over h units, giving me another input point to go into the function. And now I assemble the slope and get my difference quotient. Driving h to 0 is a problem because I have h in the denominator, so I can't just make it a 0. Can't divide by 0. So we'll do some algebra to see if we can get rid of it. I expand, collect, and factor. H over itself is a 1, so it's 2x plus h. Now I can drive h to 0, and the answer is 2x. Another way of saying the exact same thing is x gets squared, then differentiated, and I get 2x out. Let's do the cube. X and the cube are being differentiated, so I set up my difference quotient, expand, collect, and factor. Anything over itself is a 1. And now I can drive h to 0. Now there's my answer. Does this pattern always hold? Let's look at the general term we need to expand. Pascal's triangle is what we're using for a quick way to get the expansion terms. Let's just look at the 4th power. I expand. Power is the same number as that first h term. So I'll subtract x to the 4th from my difference quotient numerator, factor out, and so that first term is the only term without an h. So once I drive h to 0, that term is the only term that remains. So it looks like the pattern holds. Going to the nth term, Pascal's triangle, the first 2 terms, and then all the other terms have higher powers of h. So when I divide by h and drive h to 0, only that term remains. So the derivative of the nth power, n x to the n minus 1. Fractional powers and negative powers have to be treated a little differently, but the pattern will still hold true.